All right, here we go. Let's take a look at the next section here. We're going to start taking a look at rational function and wholes. It's so good it got a whole section. Boom, use that joke twice now. I love it. All right, let's take a look at a graph here. So I love looking at graphs. I can see the hole right there is that circle. So it looks like when x is 3, we've got this problem with the graph. So we've got this hole. And again, we're just going to define this with limit notation here. So we're going to kind of say, okay, as I approach 3, this whole idea from the left, so follow your graph, coming along, chilling. What am I approaching? I'm approaching 1 here. So I'm approaching 1 from the left. What about as I approach 3 from the right side? So if I'm coming this way, what am I also approaching? I'm also approaching 1. So we're back to these one-sided limits here. Last time we looked at vertical asymptotes. This time we're looking at holes. And again, I'm going to type this out down here because my handwriting is a little rough. Okay, so it approaches 1 as I come in from the left. And over here as x approaches 3 from the right, what's happening on the right side? It too is approaching 1. The function approaches 1. Awesome. So we're just kind of throwing some formal limit notation in there with a hole. Great. All right, let's take a look at the next example here. So the last one we did graphically. Let's try to do this one algebraically, and we'll look at the graph at the end here. But let's go ahead and find the holes of this bad boy. So what do we got to do? Well, we got to factor this. So what are we going to get here? On bottom, what multiplies to -6? I think we're going to say +3 and -2. And then what's happening on top? Pull the greatest common factor. What number divides both of these? We can take a 10 out. If I take the 10 out, what's left? There it is, x plus 3. So there's the hole because it matches. So we know this is causing the problem. Whoopsh, whoopsh. And where's that happening at? That's going to happen when this is -3. So that's where the hole is. So I want to find the coordinates of this bad boy. So I know it's at -3. The problem is I don't know the y value. So we just got to go back up to the equation. And what's left over here? So I cancel these factors. So what's left over? Just that 10. How about on bottom? The x minus 2. So without the hole, this is the equation we have. So what can I do? Just plug that -3 in. We know x is -3, so we're going to plug that -3 in there. So we're going to say -3 over -2. Oh, I'm going on to my graph. Oh, man. And that's going to be -5. So what is the y value? It's just happening at -2. So I can erase this. I found this. And where's that happening at? We know -2. Then let's make sure I'm right before I go ahead and do the limit notation. Let's go ahead and, there's the graph. I went ahead and threw the graph up there for you. You can pause and copy that down if you like. And was I right? Sure. At -3, -2, there's a hole. So I like to look at the graph when I do that function notation. I'm sorry, limit notation. So what am I saying here? You're going to say, hey, what happens as I approach -3, the x value, from the left side of this function, which be careful because he's the g of x now. And then what's going to happen as I approach that function to -3 from the right side? So from that plus side, the right side. So you don't need the graph to do this. If you know what's happening at -2, you know the answer. Like you just got it. It's -2 and it's -2. But if you want that visual to see it, here I come in from the left. I'm approaching -2 down here. You can see that -2. And if I'm approaching from the right, -2. Awesome. Rock and roll. Same example here. I just want to make a table of values. So could we do it with a table of values? Sure. Here I am approaching 3 from the left. Here I am approaching 3 from the right. So if you want to look at this, you're approaching what? We're saying x is approaching -3 from the left side. It does get kind of weird with negatives. You know, you want to be farther away from 0 to be more negative, or from the left. And then if you're closer to 0, you're actually approaching from the right. So that is a little weird to think about. But don't stress. You're cool. We're all good here. So of the function. So again, this is the same thing, but you're proving it with a table of values. Let's just do it real quick. I went ahead and I think I preloaded this. Let's see how prepared Mr. Brust is today. Boom. Preloaded. And then you can go to your table. Again, if you're not in the right mode, just go second window, which is table set, and make sure the independent variable is set to ask, because we're going to ask it questions. So let's go ahead and can we fill out this table first? -3, so -3.1. If you need to pause me, put your equation in, catch up, that's cool. I'm going to keep on rolling here though. So plug that one in. We're going to plug in 3 point, how many zeros? 0, 0, 1. There we go. And then I'm getting super close, -3.0001. So, okay, the whole idea is we're getting closer to -3 from the left. Check it out, your calculator already rounded, so be careful. Up here, it says -3, but really I typed in -3.001. It will round at some point, which means this answer over here is probably rounded. Yeah, it's telling you -2 at the quick glance, but you have to put your cursor over it to see that it's actually 1.9999. Very, very, very close. Same thing here. I mean, these are so close right here. So what's the change here? It barely changed a little bit at all. So let's fill these bad boys in to our table. Actually, I'm going to kind of cheat if that's cool. Okay, so let's fill this in. I got 1.961. Let's get the general idea here. I've got -1.996. It's not really -2. It's 1.9996. And then the next one is not on there, but I know it's like 1.99996 or something like that. So ideally, you can see as I get closer to 3 from the left, what is the function doing? It's getting closer and closer and closer to -2. Awesome. Let's do it from the other side now. So can we do it from, as I approach from the right? So I'll slide this bad boy over. Let's go back up here and clear all these out. And again, we've been doing this. We did this for vertical asymptotes. So we're doing the same thing, but now we're checking it on a whole. So as I come in from the right side, -2.99, I'm getting closer and closer. -2.999. So sensitive. Get that extra 9 there. And then -2.1234. Awesome. Just double checking. And again, I feel like it's doing some rounding already. The calculator wants to tell you it's -2. It's not really. It's very, 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 very close. And again, this whole idea is just so we're cool is if you did type in -3, it can't exist. That's an error. That's a hole in the graph. But you've got numbers like this. This one, I am just going to steal and put it in here and leave it as a table. And you can kind of see what's happening here. I'm getting so close to -2. So I'm going to put in -2 here. So you may have to just highlight over here, hover over to see the real points to type in. Awesome. And again, just so we're cool, when you go back to that graph, oh, I thought it popped right up. When you go back to that graph, we can see what's happening. I'm approaching -2. So you can use a graph, you can use a table, and to see what's happening with your limit. Awesome. All right, let's take a look at example 3 real quick here. So we got a rational function here, but check it out. This bad boy is already factored for you. If there's no grouping symbol, everything on bottom is grouped. So right off the bat, I can see, oh, there's a problem at -1. So I'm sorry, problem at 1. So if I put 1 in there, I'm going to have that whole because they both cancel. What's left over here? Well, the leftover part, after I factor it, is just this. It looks like a quadratic. So kind of cool here. Sometimes we go from those crazy pictures of those rational functions with all those asymptotes and all that. But you don't have to have all that stuff. It could just, when the hole's in there, turn into a regular quadratic or linear function or any kind of polynomial there. I went ahead and threw the picture up for you. You can see it's a quadratic with a hole there. Let's just get some closure on this bad boy because I knew the hole was at, I knew I had a hole at, what, 1? What is the y value? This happens without the graph. You just plug that 1 in. Remember, just plug that 1 in for x to get that y value. So we'll plug it into that quadratic, the leftover piece right there. And it looks like we should get -1 plus 2 plus 4 should get us up there at 5. Does the graph confirm it? It does. Then just make sure you're cool with that notation. The main thing here is this notation. So as I'm approaching, what, 1? And from which side? Let's start from the left. And again, my function is the g of x. And then over here, same thing. As I approach 1 from the right of my function, boom. I know it's approaching 5. I've got the algebraic proof. I've got the graphical proof. There it is right there. Excellent. Fantastic. Excellent. Here's the formal definition of them. We've had one every time with a polynomial divided by a polynomial is a rational function. And then we're talking about multiplicity in the next one here, about how does it find a hole as long as it cancels the top and the bottom. The multiplicity is not bigger on bottom. We're cool. All right, let's put all this together and see what happens here. We're going to do it all. We're going to go for the glory here in example 4. I always start these rational functions off by factoring. So on top, it's not really factoring. I'm actually expanding. So if I'm squaring the top, it's just x minus 2 twice. I'm timesing it by itself. What multiplies to 12 and gives me 4? I think I'm looking at 6 and 2.
Is that coolio? That works right there. Fantastic. Awesome. So that'll help me with the domain. Remember, the domain is the bottom can't be 0. So it looks like I'm going to have issues at -6 and +2. So everything's cool here to -6, then from -6 to 2, then from 2 to infinity. Those are going to be my domain issues right there. All right. How about, are there any holes in here? Yeah, I think so. We've got this x minus 2 cancels this x minus 2. That's going to cause a hole at 2, but I need the y value. So let's go ahead and see what's left over. If I didn't have that hole in there, I can graph this. I can put this in technology and graph it. If you just graph this part, though, it won't show the hole. If you put the original in there, there's going to be a hole. Sometimes you got to be careful. It doesn't really show up so well, but there will be a hole there. If I graph this, there'll be no hole. All right, let's put 2 into this bad boy. So if I put 2 into the top, ooh, this is kind of weird, isn't it? So we were going to say 2 in the top, put 2 in the bottom, and I'm looking at 0/8. So what is that? It looks like there is a 0 here. So it happens when y is 0. Interesting. Maybe you caught already because I put multiplicity on top. So I've got this multiplicity on top. So yes, the hole is there, but it doesn't affect us. If I look for the zeros, like you may have said, hey, when does the top, let me change colors here. I'm too excited. I got to slow it down. Mr. Bust, slow it down. Here we go. When does the top equal 0? Well, it happens at 2. I mean, 2 again if you want. But the problem is because there's a hole there, there is no 0. None. Because of this right here. Because of the multiplicity, the hole caused it. So yeah, I know that's going to give you 2, but this is causing a hole, so there's just a gap there. Awesome. Let's move it on to vertical asymptote. So I know that one was the hole, so I think I'm going to have a vertical asymptote here at what? -6. And then the horizontal asymptote goes back old school. Let's go old school for a little bit. If I multiply this out, what's the leading coefficient? They're both x squareds, and they've got a 1, so we're going to have that asymptote at 1. And then can I just wrap it up with some in behavior? Notation's key here. So as x is getting infinitely large, just be careful. I'm looking at the h of x. It's going to approach that asymptote. If I put infinity in there, because I've got x squared over x squared, it's got to be positive. So I know that's approaching 1. Check it out from the left side. If I put negative infinity in that problem, what's going to come out? It's also 1. Man, that is cool. That is great. Let's see that graph just to make sure everything lines up nice and neat. Oh, I wrote all over it. Can I erase this real quick so you can see it? Check out the graph. Vertical asymptote at -6, horizontal at 1. We got the hole where that x-intercept was. We got the domain. I think we crushed it. Great job with this one. Good luck on the mastery check. Peace out.